In our earlier lecture, we studied how the earth attracts every object in this universe towards the center of the earth with a force known as gravity. Now, you would be surprised to know that this phenomena of attracting objects to its center is not specific to just earth. In fact, every object attracts every other object in the universe. Yes, every object attracts every other object in the universe. So the computer is attracting you, you are attracting the fan, the table is attracting the chair, and so on. And the force with which objects attract each other is known as the gravitational force. This phenomena of every object attracting every other object is stated in the universal law of gravitation and was proposed by Sir Isaac Newton. The universal law of gravitation states that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So let us try and understand this law mathematically. So what this law is trying to state is that if we have two objects, say A and B, the mass of A is m1, the mass of B is m2, and the distance between A and B is r. Then A and B attract each other with a force known as the gravitational force, and this force is directly proportional to the product of the masses of A and B. That is m1 into m2. Further, F is inversely proportional to the square of the distance between them. That is 1 by r square. So, F, that is the force of attraction between these two objects, is directly proportional to the product of their masses, m1 into m2, and inversely proportional to the square of the distance between them. That is 1 by r square. So we have F is directly proportional to m1 into m2 and F is directly proportional to 1 by r square. Now combining these two, we can write F is directly proportional to m1 into m2 divided by r square. Further, we can remove the proportionality sign by introducing a proportionality constant. So F is equal to G into m1 into m2 divided by r square, where G is known as the universal gravitational constant. Note that G is a constant here. G is independent of the masses of the two objects and it is also independent of the distance between the two objects. Now, what is the SI unit of G? Well, F is equal to G into m1 into m2 divided by r square. We could rearrange to get G is equal to F into r square divided by m1 into m2. Now, the unit of force is Newton. The unit of r, which is distance, is meters. And the SI unit of mass is kg. So, the SI unit of G would be equal to Newton into r square, which would be meter square, divided by mass into mass. That would be kg into kg. So, the SI unit of G is given as Newton meter square divided by kg square. Now, what is the value of this G? That is, what is the value of this universal gravitational constant? If we have two objects, A and B, of masses 1 kg each, and if they are placed at a unit distance, that is 1 meter apart from each other, then what would be the value of F? Well, F would be equal to G into m1, which is 1 in this case, m2, which is 1 in this case, divided by r square, which is 1 square in this case. So what we get is G into 1 divided by 1 is equal to G. So F is equal to G. Hence, G, or the universal gravitational constant, is numerically equal to the force of gravitation which exists between two objects of unit masses kept at a unit distance from each other. And this has been found to be 6.67 into 10 to the power minus 11. And since we've just studied that the SI unit of G is Newton meter square per kg square, so the value of G in SI system is given as 6.67 into 10 to the power minus 11 Newton meter square by kg square. Now we can substitute the value of G in F to get the universal law of gravitation in the mathematical form, which states that F is equal to 6.67 into 10 to the power minus 11 into m1 into m2 divided by r square newtons. The unit of force is newtons. Now if all objects attract each other, then would we expect that this bat would attract this ball and the ball would vice versa attract the bat in such a way that they would come close to each other over time? Well, let's find out the force with which these two attract each other. So the mass of a typical bat is approximately 1 kg. The mass of a cricket ball is approximately 160 grams. For calculation purpose, let us assume it equal to be 200 grams. So this is equal to 200 grams or equal to 0.2 kg. And let us assume that they are at a unit distance from each other. That is at a distance of 1 meter from each other. So let us find the gravitational force of attraction between this bat and this ball. We know that the gravitational force of attraction is equal to 6.67 into 10 to the power minus 11 into m1 into m2 divided by r square. Let's substitute the values here. We get 6.67 into 10 to the power minus 11 into mass of the ball, which is 0.2, into mass of the bat, which is 1, divided by r square, where r is the distance. We've assumed it to be 1 meters, so 1 square. And if we calculate this further, what we would get is F is equal to this number, that is 0.1334 into 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minus 10 Newton. So how big is this force? Well, with this force, the bat and the ball would take approximately 400 years to cover that unit distance of 1 meter. And that 400 years is when we have ignored the frictional force, which would oppose their coming together. So you can now understand how small a value of a force is this. And hence that is why we don't see things moving to each other. So the universal law of gravitation states that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And mathematically, we can write it as F is equal to 6.67 into 10 to the power minus 11 into m1 into m2 divided by r square, where m1 and m2 are the masses of the objects and r is the distance between the objects.